For those of you who don't know me, my name's Gavin Brooks. I'm Deputy Vice-Chancellor here. It's my real pleasure to be able to introduce Dame Julia Slingo and obviously to introduce her lecture, which is a part of a wider activity that we've had this afternoon. We started just now with the renaming of this lecture theatre into the Slingo Lecture Theatre, which is in honour of Dame Julia Slingo and her husband, Professor Anthony Slingo, both of whom were esteemed members of the University of Reading community. I'm delighted that Dame Julie's here. She's going to talk to us in a moment about how climate science has evolved over the last 45 years. I don't think she's necessarily been involved in all of that 45 years, but possibly all of it. Okay. That's probably right. There you go. And it is a really impressive career, as I'm sure many of you who know her will already recognise. She's brought innovative approaches to our understanding and modelling of weather and climate. She's developed complex weather and climate models to deliver new insights into how the atmosphere and climate system works. And this includes significant advances in predictive skills and climate services. Through her career, she's worked in a number of organisations, including the European Centre for Medium-Range Weather Forecasts, the United States National Centre for Atmospheric Research, and also here, of course, at the University of Reading. Dame Julia was appointed as Professor of Meteorology and also Director of Climate Research in the NERC National Centre for Atmospheric Science here at Reading. In 2006, she also founded the Walker Institute for Climate System Research that continues to thrive here to this day. Following this, when Dame Julia left the university, she served as Chief Scientist at the Met Office for 7 years, and then she retired in 2016. But just talking to her now, just now, she certainly hasn't retired. She's certainly giving a lot of her experience and talking to audiences like this around the globe. When she was at the Met Office, though, she led a team of more than 500 scientists working on an extensive range of research topics. And in retirement, she's taken on several roles, which include as Special Advisor on Science to the Secretary-General of the World Meteorological Organization and as a member of the NERC Council under the UKRI. And it's a real pleasure, as I've said, to have you here today to talk to us about such an interesting topic. So just before I hand over to Dame Julia, I'd just like to make you aware that we are filming the lecture, so please make yourself known to any members of staff if you would not like to be on that film. And I suspect that will mostly be in the Q&A session rather than when Dame Julia is giving her presentation, because I think we'll be focusing on you during that period of time. So it gives me great pleasure now to hand over to Julia. Thank you.
So, yes, how to do the changing face of climate science in 30 minutes. It may not be quite 30 minutes, might be a bit more. I chose this picture on here because those of you who were with me in NCAS Climate and before that in CGAM, we used that image once in one of our science strategies, so had to come out again. As Gavin said, I started my career in the Met Office in the early 1970s. It truly is more than 45 years ago. And working on building the first climate models at the Met Office, writing the radiation and cloud schemes, and using them as tools to understand how the climate worked. And so I've watched climate science evolve over 45 years. And it has indeed gone through an amazing transformation, which is what I will cover this afternoon very, very briefly. As I said, and in that time, of course, it's changed from something that was of academic interest to something that is of global political, social and economic interest. And that in itself is also an amazing story, which we won't have time to talk about very much this afternoon. So first of all, let's look at what has transformed climate science in the 45 years that I've been in it. And of course, all good science starts with observations. And this has been truly a major transformation of climate science. And when I first showed up at the Met Office and we were trying to assess how good our climate models were, we had a book of pictures of the general circulation by Abraham Ort, I believe. Brian will remember because he's old like me. And based on just some summer and winter plots of what they thought the general circulation was like from meteorological observations. That was all we had. And I was writing cloud schemes looking at radio sond ascents. And we were just beginning to get the first really interesting satellite images which showed us roughly where clouds were over the planet and what they looked like. Now, of course, observations tell us an immense amount about the climate system and how it is changing. It's hard to imagine a world without them, but that was pretty much where we were 45 years ago. But of course, they just tell you what's happening at the end of a whole complex set of interactions and feedbacks and processes in the climate system. So they don't necessarily tell you how the climate system works and why it is changing in the way that we observe. And of course, that takes you immediately to what has been, I think, the major second transformation of climate science, which is climate models, which is where I started my career. And we have to say this more and more, even today, that climate models actually simulate the climate system based on fundamental laws of physics. The number of times you still meet people who think they're empirical models that are somehow analogues of observations. That is absolutely not true, and I don't need to tell you, all of you, that. And I think they've been one of the great achievements of modern science, which we don't celebrate enough. It seems to me extraordinary that with really only the constraints of the input of solar irradiance, plus the rotation rate of the planet, which determines most things about our general circulation, and the geography of the planet, the land masses and the mountains, those fundamental constraints give you pretty much most of the general circulation. Quite sobering to think about that. And that everything else that comes out of these simulations and what you saw when you were sitting waiting for the lecture to start was a simulation. One of the groundbreaking ones done by Len Shaffrey, Pierluigi Vidali and others here at 10 kilometres, an astounding resolution when we think about weather forecasts, global weather forecasts, barely at 10 kilometres, and here we are running. But that was a simulation with those constraints, some fundamental physics, and out of it comes all the richness of the weather, the natural variability, El Niños, monsoons, thermohaline circulations. I just think that is an amazing achievement. So climate models help us to explain how the climate system works, and I guess I built my career on using models as laboratories to understand different aspects of the climate system. I think it was one of the hallmarks of Reading's expertise in climate science over many, many years, and I think it probably still continues to be. And of course, what our future climate might be like. Of course, none of this is possible unless you have big machines. And so actually the third transformation of climate science has been supercomputing. And this is just a selection of machines that I have directly played on or helped other people to play on during my career as a scientist. And I think it's fair to say that the development of climate science has been defined in many respects by our access to supercomputing power. Many of us knew way, way back when I was doing my first cloud parameterization schemes that if only I had more resolution, I could have a better go at this. But actually we could barely run a constant January and a constant July simulation. And I was remembering back with Lois when I came back to Reading in 1990 and we decided to enter the first atmospheric model into comparison project, AMIP, as an independent modelling group, that Lois had to go to Lawrence Livermore Labs to run the simulation. So we were hunting around always to be able to be somewhere near the cutting edge of climate science. So here we are, there's the Cray one at NCAR. What you'll notice is that these machines get bigger and now they're getting smaller again. So they weren't that big in the beginning. And then Pierluigi, who's here, came specifically to go and run models on the Japanese simulator, which was a massive machine. The hall was the size of a baseball pitch, I recall. I can't remember how many cabinets were in it, but there were a lot. But this was the biggest machine in the world, so we went and we used it. Then there's the Met Office IBM Power, whatever it is. I think I've cut that off, but that was the machine that was there when most of the time I was chief scientist. And then I and others managed to persuade the government that they might like to part with close on £100 million for a proper machine at last to do weather and climate science. And even this, in my mind, wasn't big enough actually to do the sorts of things that we've just been looking at. And these things are really important for understanding how the climate system works. And I would argue how it's going to change. So supercomputing has been a transformation of climate science. And we need to keep fighting for more and more of it. And I remember when John Beddington was government chief scientist and I'd come in to talk to him and he'd go, oh God, I know what Julia's going to ask me for. But in the end, we won through and we got a major hike up in power. And then, of course, the fourth transformation, of course, is global warming. So I joined the Met Office in the early 70s when the CO2 concentration was round about, well, I think we used to put 320 in the radiation code at that time, but it was around about 340. And I remember writing a little paper with Peter Roundtree on climate-sensitive cloud and water vapour feedback in a 2 times CO2 world in the mid-1970s. And it went into a book called Carbon Dioxide, Climate and Society, which, I thought was just a bit of fun. It was quite an interesting way to flex the physics of the model in a single column and try and understand some feedbacks. It wasn't far off the mark, actually, but who would have thought that 40 years on, carbon dioxide would be at 420, right? And that climate change would be one of the great challenges of the 21st century. And so we have the IPCC, which I think is arguably one of the greatest services by scientists to humankind and the natural world. Not everybody would agree, but where else in science do you get 1,000 scientists or more coming together to work on something like the IPCC, going through tens of thousands of papers and addressing God knows how many reviewers' comments and coming out with something that is of the highest integrity. So I do really fundamentally believe that IPCC has been a massive service to the world and, not surprisingly, got a Nobel Prize for it. And I'm very fortunate to have Tony's Nobel Prize certificate on my wall in my sitting room. But as I wrote recently, it would be wrong to conclude that climate science has been taken over by the politics of climate change. That is absolutely not the case. Nevertheless, climate change presented significant science challenges that would have not happened otherwise, I believe, without that, and has, in my view, accelerated the progress of climate science. We've had to delve into questions that I don't think we would have done at such depth and at such pace without the challenge of global warming. And so in many respects, if we come to today, we see climate science coming of age within what I call the 21st century changing landscape of climate risk. And in 2015, we had three, I think, major things happen. We had the Paris Agreement, which of course is all about limiting global warming. But we also had the UN World Conference on Disaster Risk Reduction, the Sendai Agreement. And that's where, of course, weather and climate prediction, the seamlessness of those, really comes into play. And here you don't need to invoke climate change as to why you need climate science, because short-term climate prediction can make a real difference about how we manage disaster risk and help particularly those in the developing world. And then, of course, we've got the UN Sustainable Development Goals, addressing so many aspects of challenges, particularly for the developing world. And if you look at pretty well all of those, in there somewhere is weather and climate science. You can't tackle those challenges without it. And you can read the bit in the middle. But I think this other figure is something that I've used an awful lot over the last few years, because it's really important that we remember that our science and the challenges we address have to be seen within global issues about all the securities that we rely on for our health and well-being and our livelihoods. Water security, migration, health security, food security, all those things. And all those, how we manage those securities in the future will all depend on how we manage the things in the dark blue circle in the middle. And amongst those, of course, is weather and climate variability and change, but it's in the context always of what other things happening in our world: urbanisation, population growth, limited natural resources, of which fresh water will surely be one of the most demanding. Water will arguably become the most precious resource on the planet in the coming decades. So we fit right in the hub here, the nub of these massive challenges that we face for the 21st century. We need to learn how to shape our science to reflect that positioning and this more holistic view of this interconnected world that we live in. And of course, it's not surprising that, therefore, in my view, that the World Economic Forum in Davos last year plotted that what they thought the impact and likelihood was of major risks, which include environmental risks. And there they are in the top right-hand corner, the most likely and having the biggest impact on world economy. And the top one, you won't be able to read it, says extreme weather events. The next one down is natural disasters. And the next one down is failure of climate change mitigation and adaptation. So here we are, meteorology across weather and climate is hugely important. And of course we have some new tools in the toolbox. And many of you will know these figures. They're Met Office versions, but it doesn't really matter. This ability now to predict seamlessly across timescales. When I started, and actually pretty much when I entered the Met Office as chief scientist, for 30 years we had the weather forecasters working at the short end and we had the climate folk working at the far end. And we didn't really do much together in between. But actually, over the last decade, we've really filled in this bit that's this monthly decadal bit, which is where actually most people make their decisions. And I think now this ability to provide predictions across all timescales has an immense value when we look at those big challenges that I just talked about. And of course, Brian's here. He and I understood this seamless stuff a long, long time ago. But it's taken a long time to get into place, hasn't it? So it's an exciting time. Of course, the other tool in the toolbox is seamless prediction across space scales. And this is now where we have, I think, certainly in the weather community, this has been now well established. And in the Met Office while I was there, we saw the implementation of the 1.5 kilometre UK model for short-range weather forecasting, and it was a revolution, actually, in our ability to forecast weather at the local scale. There is no doubt about that. But actually now we're beginning to use them also in climate prediction, and the UK CP18 some of which is published. The global part is published using a Met Office model at 60 kilometres, so pretty close to this as part of it. Later this year, the high resolution 2.2 kilometre resolution scenarios for the UK will come out. And if that isn't the use of seamless modelling across, in this case, space scales and across time scales, then I don't know what is. It's that fertilisation of what we learn from weather forecasting being carried through into how we must assess future climate impacts. And it's allowing us gradually to build a really consistent pathway from weather and climate hazard through to impact. We're not there yet, but I think the tools are in the toolbox now at our end to enable us to do that. So I think that's a really exciting possibility. So that all sounds wonderful, doesn't it? But of course, it's not really, because there are actually some really fundamental questions remain unanswered. We don't know where all the heat goes in the climate system. We learnt that when we faced up to the pause in global warming. We didn't really know what the oceans were doing and how they were taking up heat. We still don't know what the climate sensitivity of the planet is, really. There's still a large range of uncertainty. We don't know where all the fresh water goes. We certainly haven't closed the hydrological cycle. We need to have a whole generation of hydrometeorologists to do that. And I'm not going to talk about this, but we actually don't know where all the carbon goes, partly because we don't know where all the fresh water goes or where all the heat goes. So there's some really big questions out there that we need to answer. And if Tony had been alive, he'd have had his teeth into some of these. I know he would. And so I think it's good to reflect on what he did and to remember that there is a real role for some fundamental physics using the best of observations and models and theory still to be done to tackle some really quite fundamental questions. And this was what he was after. He wanted to understand, in fact, all his career, if you look back at what he did, the interactions between radiation, clouds, dust and aerosols. And he had this wonderful ability, which is actually quite rare, of being able to go from theory to how you go out and observe these things rigorously in the field and from space, and then to take them through and to use them to challenge the models and to improve the models. And he did, I think, an amazing job in all of that. And those that worked with him, and it's very nice to see some of his old colleagues here, particularly from the Hadley Centre, is that those will know that he loved acronyms as well. So it was the age of acronyms with Tony. This was round about the time he was coming to Reading. So we had Samson, and we had Clearer, and then we had Synergy. And finally, his masterstroke, he said, was Radagast. Anybody know who Radagast is? There's a hint here, because it's on the logo. But he loved the Lord of the Rings. And he spent a lot of time talking about the Lord of the Rings. And Radagast is the brown wizard, right? He's a good wizard, but he's the brown wizard, and there he is. And he must have spent ages working out this acronym so that he could have the brown wizard. But anyway, he was very involved in when he was in the Hadley Centre in helping to design this satellite mission, which was the geostationary Earth radiation budget instrument. And why did we need this? Well, actually, because we didn't know in detail what the Earth radiation budget was, because all our estimates were based from polar orbiting satellites. Because geostationaries are only observed in discrete spectral bands. So you didn't know what the whole Earth radiation budget was. So there was this mission went up, which looked down. Of course, it couldn't do the whole globe, but actually it could do a really interesting part of the world, and was measuring the Earth radiation budget every 15 minutes, I believe. Somebody can correct me if I've got it wrong. But actually it enables some really exciting science, which is what he used in some of these early acronyms. But at the same time, he also realised that you were only looking in at the top. And actually, that didn't tell you everything you need to know. And so he managed to persuade the big program in the States on atmospheric radiation measurement to take their mobile site to Africa. And here he is at the ARM site in Niamey in West Africa. And he had an absolute ball doing this. And he's here with Peter Lamb in the striped shirt, who also has now sadly passed away. And I don't know who the guy in the middle is, because I can't remember. He was one of the ARM people. But here you were, he was in heaven, because he had all these instruments looking up and he had Gerb looking down. And every 15 minutes he had coincident observations. More than that, he took the plane, he had the plane there as well, and of course he'd started his career flying around in planes. So he also had the combination of surface, satellite and airborne measurements. And he really wanted to look at what exactly is the atmosphere doing in things like dust storms. And this was a great place to do it. And actually, there was a major dust outbreak. This is a rendered satellite image of a huge outbreak. And in a minute, we're going to see in the pink colours dust being blown and then lofted. We'll see it coming in a minute. Here we come through the middle, through the gaps in the small mountains there. Huge plumes of dust coming down over Africa. And we'll see them head out to the minute into the Atlantic Ocean and then being carried up in the circulation. It's the sort of things where we get red dust on our cars and things. So he was there looking at this outbreak and right one. And he got some really fascinating results, which I'm not going to go through. The graphs are very small. But the key point was that this was the first simultaneous observations from space and the surface of a major dust storm. And the results gave us an insight of how much dust perturbs the radiation. This is the solar radiation balance at the top of the atmosphere and at the surface. So at the surface, pretty well all the direct sunlight had gone to be replaced by diffuse radiation in the grey lines. And so overall there was a reduction in solar radiation to the surface of about 300 watts per metre squared by this dust. But actually it was the first time when I'd ever been able to calculate robustly what the atmospheric divergence was actually happening in the atmosphere, which is the bottom graph. And he didn't quite get the vertical scale right because he underplays his results here, you see. So, but what it shows is that the atmosphere is being warmed by this dust by a couple of hundred watts per metre squared, and the models were completely underestimating that. So this was all playing into this anomalous absorption of solar radiation debate that was playing at that time. I don't know whether it's been resolved. Perhaps my radiation colleagues can tell me afterwards. He was on the cusp of some great things here, and his final experiment in here was published after he died. And I always think, it raised so many actually fundamental questions about the atmosphere and its ability. How does it find radiation balance? Even when you go through a huge seasonal cycle, there's radiation balance somehow or other. It was fascinating. And I think, we miss him because we miss people who are able to think of a great field experiment that is immediately applicable to a big problem that we have in the models and in understanding the climate system. And it's important to remember in the models that a lot of physics goes on at scales much smaller than the model grid scale. So though I said at the beginning, the fundamental constraints on the Earth, on the general circulation, can give us lots of answers. And it's certainly true that the very early climate models that we worked on in the 70s, we had 75% of it was about right, actually. We didn't get some of the fine scale, the precipitation right, but actually we've got many of the bulk properties of the general circulation. We're not far off wrong. But of course the devil's in the detail. And the devil is still in the detail of this box here, really. Cumulus convection, precipitation, clouds and microphysics. We're still struggling with cloud feedback for climate change. We're still not very good at precipitation distributions. Now looking at actually intensity frequency type things. They don't go away, so we still need the Tonys of this world to come and help us do that. And of course, I came to Reading and was extremely interested in this thing called the Madden Julian Oscillation. And my interest was tropical climates, but actually I very early on learnt that to do tropical climate, you needed to do tropical weather. And I think, Mike, somewhere here, we wrote a very early paper on looking at convective parameterisation in terms of its tropical weather, not the mean state, because actually that wasn't terribly interesting, but the weather was very interestingly different. This thing called the MJO, we're going to watch about 10 days of this. It's a wonderful example in May 2002. And you start with the Indian Ocean full of cloud, and it spawns all sorts of wonderful things that we know as cyclones tied up with equatorial wave theory. And then by the end of those 10 days, the Indian Ocean was completely empty of cloud. This is the MJO, and we're still not very good at it. Are we? Don't think so. It comes, it goes, as far as I know, in climate models. But embedded in that was all sorts of fascinating physics that we needed to understand. And so me and my research group, many of whom are here today and still driving forward on this, was that we spent about 17 years trying to understand all these different bits of the tropical variability. And that actually, of course, it's all about scale interactions. And that actually, if we want to do the tropics, we need to do something as basic as the diurnal cycle. And we've only just about cracked that when we get our models down to about 4 kilometre or less resolution, which is interesting, isn't it? But anyway, very complicated diagram, but the point is that this is a highly complex system and you have to take it in chunks. And we did some great stuff with Brian on equatorial waves and coupling of physics and dynamics. We did great stuff with Eric, who's here somewhere, on MJO and ENSO. And all those things, and westerly wind events. But here we are, this is a complex system. But at the end of the day, it all depends on how we represent these things in the models. And so we come to what I think was another great breakthrough towards the end of my time at Reading, was this realisation that we actually had this capability now to use models as laboratories. And that we could, to understand convection, use a very fine-scale version of the models at sub-kilometre and kilometre scale, particularly at the kilometre scale, over large domains, where the behaviour of the model is not constrained by the boundaries. It wasn't that this work wasn't going on up till then, it was. But actually, a lot of the solutions were constrained by the boundaries because the domain was so small. The breakthrough here was being able to actually have the compute power, and it wasn't easy, over these large domains. And this simulation here is just a bit of a gratuitous one, really, but it's a typhoon done at 1.5 kilometre model. From a real initial state, it's a fantastic simulation of a typhoon. And what you see emerging from the raw initial condition is self-organisation of the clouds and the development of the typhoon. So this is physics happening in the models. So the idea was that we could use these models as laboratories and go in there and understand the physics. And out of that came a joint programme called Cascade, which was joint for the first time with the Met Office. And I went to NERC to argue the case with a Met Office colleague, Roy Kershaw. And NERC said, well, if the Met Office are interested in this, surely they can do it. But actually we managed to argue the case, and where is Steve? Steve's somewhere here. And Cascade was funded, and it was a hard project. And of course, you know, we learnt from that that actually this is a very, very complex issue. But we learnt some important lessons that set us up for the next stage. We learnt that we need to to deal with upscale energy transport in convection, and how the self-organisation of convective systems works, such as the role of gravity waves. We need to think about how we design stochastic physics within our subgrid scale parameterizations. We need to think about convection not as being a single time-step adjustment process, but that convection evolves over time, and that in that evolution it preconditions the free troposphere to build deep convection. They were all things we kind of knew, but we'd stepped back from them because they're difficult. And so you come to the conclusion that you need a radical rethink of convective parameterization. And now, of course, the Met Office steps up. We have a joint programme with NERC, or they did, I'm not there anymore, called Paracon, which is about 2 years in, involves NCAS and Reading, and I'm very, very deeply involved. I know the folk here are. And I saw the latest results from that a couple of days ago, and there's some really innovative, creative thinking about how you write a convection scheme. Just throw the old ideas away, come up with what we really know about convective clouds and what they do. So this is fantastic. I think we're actually making progress. And then, of course, I couldn't actually not give this talk without talking about high-resolution model. Because I guess all my life, I was trained as a meteorologist. All my life, I've understood that actually what's really important is the weather. It's not the time. The time mean climate is actually just made up of the weather. And of course, coming to Reading and working with Brian, it was very clear that if we were going to do climate, we needed to do weather. And then you come to the inevitable conclusion that actually the climate models can't do weather when they're running at 300-kilometre grids, or even a 150-kilometre grid. And so we had this bold proposal with NERC, other NERC colleagues, to build a high-resolution climate model. And I won't tell you who it was, but I went into someone who I was working for at the time and said that this is what I wanted to do. And he turned around to me and said, well, that's a complete waste of time, Julia, because you can only do one simulation. And we now know that you need to do a whole ensemble, because it's all about probabilities. So I said, well, yes, but actually a whole ensemble of poor simulations is of no value whatsoever. And I think we'll learn a lot of things by doing one high-resolution simulation of how scale interactions work and how the weather drives ocean-atmosphere interaction, all these things. So that was how we all started. We got access to the Earth simulator, and we started the first 90 kilometres, yes, folks? Then 60, yeah, 90 kilometres, which we thought was pretty exciting. And they began to look quite exciting. And we had HiGEM, which then became the NERC programme that was funded in this area. The two ran along in parallel, sort of. But HiGEM, we were able to really flex the model resolutions. This is just a wonderful picture, not entirely from HiGEM, I think. It's got a 12-kilometre model in there. Pardon?
It's HiGEM.
HiGEM, yes. But just emphasising of the importance of resolution, in this case for atmospheric flows. So 130-kilometre grid, IPCC AR5 resolution, doesn't look like anything, really. It's completely diffuse, not very interesting. This is humidity, by the way. 60 kilometres, which will be a bog standard AR6 model, I think. It's getting a bit better. But if you're really interested in water vapour and its transport and how it gets carried in weather systems, then you might want to be down at 12 kilometres. Or even more. So HiGEM was a very bold programme, but we did make some, I think, breakthroughs, be able to show that we could improve the mean state of the tropical Pacific and thereby ENSO, and storm tracks and blocking and various other things. But it was still, I think, quite tricky. Of course, in the ocean, The results are far more spectacular in a way because ocean eddies are much finer scale than the atmosphere. So you don't have a hope in hell really at 80 kilometres doing anything very interesting. Just looks like a bit of a mess really. At 20 kilometres, which is where we'll be with AR6, quarter of a degree, beginning to look actually like an ocean. And these are the latest stuff coming out of the very high resolution work being done in this case in Helene Hewitt's group and in your programmes, Pierluigi, I'm sure, the joint programmes, where actually you begin to see some really fascinating things in the ocean. And these things matter because actually this is where the ocean, where the ocean biology works, is where these eddies are. And these eddies are taking heat, they're taking nutrients, they're taking down the carbon, they're doing all the things that we need to know about for climate change. And then, of course, finally, we get towards where we were showing at the beginning. I'm not sure whether this is triply upscale and priced, but it doesn't really matter. This is another story of going out to get computing power from a consortium of European supercomputers. And the upscale project managed to get an enormous chunk of it without actually having put anything in. It's very enterprising, actually. But there we are at 10 kilometres, and I understand Pierluigi tells me there's now a 5 kilometre run on the go. So this is a major story for me. This is about, at long last, us getting down to weather-resolving scale and understanding that these are the building blocks of the mean climate. And finally, here we are, Reading influence, I would say, Primavera, which is a huge EU programme being led jointly, I think, by the Met Office and Reading, right? To do this on a European scale and really pushing the boundaries of these simulations. And so we have two stories here, and this is really important for me to tell these stories, of what were bright ideas 20 years ago, or even longer, 30 years nearly, that I came to Reading, of tropical weather variability being a fundamental part of the tropics, of weather being fundamental part of the climate, and having these ideas over the following years of how we can flex models to really break some barriers in understanding, and how these ideas were just blue sky thoughts 20 years ago. And we were a bit bold, and we threw these proposals like HyGem and Cascade at NERC. Who funded them? And here we are with Paracon, biggest programme in the world dedicated to convective parameterisation, I would argue. Huge investment, 10 million. And Primavera. All from, so the key thing is here is, it's pity NERC's not here. It's really important for research councils to understand that the path from a bright idea to full impact and implementation is often 20 years. It's not tomorrow. And you can never anticipate the journey that you'll take when you go with these blue skies ideas. And so I think that's a message we keep needing to give to those who fund what we do. So that really brings me to the end of this talk. I mean, I nicked this nice picture from WCRP because I've been reviewing their programme. 3 things that I think have marked out what we've done at Reading in my time here and then subsequently at the Met Office. This coalescence of weather science and climate science. I think we've achieved that coalescence. I really do. And that high-resolution modelling is driving major breakthroughs. I think we've shown that. So the arguments for more supercomputer power is more and more compelling, actually. And that we've got to build the models to exploit it effectively, because we have to do these things down at weather and cloud scales. But most of all, there's still some fundamental physics to be done. The job of the climate scientist is nowhere near done, even though some people in the climate change world may think that we're now largely irrelevant. That is not true. And so I'm going to sort of almost leave the last word to Tony, because this is a wonderful photograph of him, taken actually not long before he died. And I can look at this and I can see him saying, "What? They're naming a lecture theatre after me? Oh, what larks, Julia, this is great fun." And I remember that he said to Graham Stevens when I was appointed chief scientist, he said, "The girl's done good." So I think he would say, we've done good to be here doing that. And so I think at the end of the day, the changing face of climate science over the last 45 years for me has gone from one of sort of just an intellectual interest and actually a bit of a challenge to something that is about helping us to live safely and sustainably on our planet. Thank you very much.
Julia, thank you for a fantastic talk, and I'm sure there'll be some questions after that. So we have a couple of microphones that will be roving, so if there are any questions, you can just wait until the microphone comes to you and then everyone in the audience can hear. Questions? It's like you've sorted everything out in climate change, but there's one down there.
No, I haven't.
No. there's one right down the bottom. Yeah.
I'm not truly a weather person, but I'm just trying to understand the relationship between higher resolution and how you gather the data, like water temperature, wind speed, radiation levels, and how that resolution correlates to the resolution of the modelling.
That's a good question. I mean, really, you have to go to weather forecasting to answer that question, because we go through what's a process of called data assimilation when we initialise a weather forecast. We take millions of bits of data, particularly from satellites, which are at those sorts of resolutions I've been showing there, and we create a fully consistent three-dimensional. And we still have balloons, and we still have an awful lot of information from aircraft, and of course the satellite retrievals give you vertical information. So actually, the whole data assimilation process of initialising a weather forecast gives you a really fantastic view of the three-dimensional structure of the atmosphere. And what's been happening in the last 15, 20 years or so is that technique has been taken back in time to produce what we call reanalyses of the atmosphere and now the oceans too, which give us a climate data set actually at very high resolution of the best estimate of what the three-dimensional state of the atmosphere has been every 6 hours or every day, going back over now many decades. And we're able to use that to verify what the models are doing. And of course, we use a lot of Earth observation to evaluate the models in great, great detail. So the combination of this transformation of Earth observation that I talked about has happened alongside this transformation of climate models. And actually, the models are now finally catching up with the quality of the Earth observation. That is also a long story of huge investment in satellite observations, and the models trying desperately to catch up. It's true that we might overtake them in future, and that's going to be a very interesting way in which how you evaluate the skill of your model when you haven't got observations at such fine scale. But I'm sure, and I have some ideas about that too, but yes, we're not short of actually, we have plenty to tell us whether the model's doing the right thing or not.
So you said that climate, or I guess, if I forget it right, politics of climate change hasn't overtaken climate science, but I'm wondering, it's raised the bar to force us to work harder, but do you think the questions being posed by climate change might change how we do the science a little bit? And in particular, I think one of the challenges of a seamless approach seems to be the tension between mitigation questions and adaptation question, you talked about the extreme weather.
Yes.
You need larger samples, you need oscillation, and I think the fact that the physical model in your Earth system model, the versions going into CMF6 are different by a factor of 2, which is not much of a difference really. I wonder if we have to treat these in somewhat different ways.
That's a very good question. I mean, I think there are two sides of the coin really on the role of climate change. I wanted to make the point that actually there are beneficial roles. Some of us see that to some extent the IPCC agenda held back the development of our science. I think that's undoubtedly true. The need to freeze model versions before they're really ready hasn't been entirely a good thing, and the whole business of understanding uncertainty and all of that has sometimes taken us off down, become an engineering exercise rather than a scientific exercise. I'm pleased to see that at least in the UK ESM, Earth System Modelling Development, that the argument that you really need the best physical climate system in which to do Earth system processes has been largely accepted, and we're still struggling, I think, really against compute power, again, as well as some intellectual issues around do we observe the right things to know whether we're getting the right Earth system feedbacks. I'm very pleased to see that programme is recognising that, and it's true there's still a gap in the IPCC, but I think that gap will close just as the gap has closed between global physical climate modelling and global weather forecasting, right? That's closed enormously in the last decade or so. On the adaptation mitigation, I think we have to distinguish between near-term climate change and long-term climate change as being different political decisions and different issues that we might look at in the models. But I would argue that actually the modelling of underpinning science has to be the same, because if one's good for adaptation, it has to be good for mitigation, because we're actually looking at addressing these fundamental questions about where does the heat go, the water and the carbon go, which is as important for climate variability as it is for climate change, in my opinion.
There's a question here.
Yes, thank you, Julia, for this wonderful collection of amazing things that you both contributed to the community. Really amazing adventures. So, building on Ted's question, maybe going more into the political world, how do you see? Obviously, we are at crossroads. The climate science has come quite far into being an essential element of society. How do you view, both from your WCRP experience and Met Office, how should we move forward in terms of in our trade? What we do as scientists, we're not people doing operational, for most of us, operational advice to society. This is asking the question about climate services. How far do we go, or we don't go? Do we integrate new bodies, or like you're using this?
Yeah, well, it sort of goes back to that figure I showed, what I call the circle of securities, and the awareness we have to have now when we do our science of the issues around us that require our science. I think there is a real risk of being diverted onto, I'll call it the impacts or service end of the value chain. Because all of us want to feel that we're doing something useful, and actually branching out into a different discipline is actually quite stimulating. I remember that when we set up the Crops and Climate Group in Reading, precursor of the Walker Institute. It was great fun to play around with the agriculturalists and learn about crop performance and so forth. And I think that broadens us, but we have to be really careful that we don't forget that there's bedrock science to do. And there will be a piece coming out, I think, in Nature Climate Change next month that I've written about the WCRP review. And that we came to the conclusion very strongly there that actually, whilst we need to be cognizant of user needs and actually have dialogues with them, it's not necessarily our job to do the work ourselves, but to facilitate it by others. Because there is a real risk that we wander off into actually things that are somewhat easier to do, I would argue, than some of the really big issues, like convection, which are intellectually really challenging. And we have a history of going off and doing something that you can't evaluate very easily or play with. Carbon cycle comes to mind. When we haven't solved the problem of the water cycle. And I think we have to be very, very clear and very determined, actually, about bedrock science and ensuring that the funders understand this. I didn't bring it with me. I have a lovely cartoon of Linus building a very complicated sandcastle. And he looks ever so pleased with himself. It's some peanuts. And then it starts raining, right? And all he's left with is a pile of sand. And he says, the message is in here somewhere, but I don't know what it is. And the point is that it's actually all tied up with the biblical little story that we all heard as children, is that the wise man built his house upon a rock. So if we want to do impact scenarios and adaptation scenarios and advise governments, we better make sure we don't build a very fancy sandcastle. And then, of course, the corollary is the foolish man built his house upon the sand, the rains came down, the winds blew, and his house fell down. So I think there's a really serious, that's a cartoon, there's a really serious message here that and I followed it when I was chief scientist, we must give rigorous advice. We must do the best possible bedrock science. Because if we don't, the whole edifice on which society is going to plan its future is just going to get washed away. So that's kind of where I'm at. Now, it doesn't always go down well, but it comes back to the point I was making earlier on, that good bedrock science sometimes takes 20 years to do. So funders need to be patient and wait and make sure that the best possible science is there. And if we can't give it them, we need to say why we can't. Or we give it with lots of caveats and be absolutely clear what the caveats are.
Okay, I'll knock that bombshell. Before proceeding to close, but enormous thanks, Julia, and of course to Tony also for the contributions you've given, not just to Reading, but to the world in terms of climate science, the both of you. Thank you very much indeed.
Thank you very much.